Hello everyone. Our topic today will be the lower complexity bound for the first order methods in solving the minimax problem. So this is a joint work with Professor Mingyi Hong and Professor Shuzhong Zhang at the University of Minnesota. So basically, the main problem that we are considering is the following convex-concave minimax problem, where we minimize over x and maximize over y for this function f of xy. And it is a convex function in x for any y, and a concave function for y. Hello?
Can you make it the full screen?
Full screen? Oh, sure. Sorry, I just forget that. Okay.
Yeah, good.
Is it okay now?
Yeah, much better.
Right. Sorry for that. And we also assume this f to be a concave function in y for any fixed x. So this is a convex concave problem. And the goal of this problem is to find an epsilon saddle point, denoted by this x bar and y bar, such that the duality gap defined this way is less than or equal to epsilon. And it is known that this duality gap is always non-negative, and it equals to 0 if and only if this x bar y bar is exactly the saddle point that we are looking for. So to solve this problem, there are plenty of algorithms, including probably the most popular ones, the first order algorithms. And sometimes if you have some special structures, you have some proximal algorithms, and they just include the gradient descent ascent, the GDA algorithm, the mirror prox, extra gradient method, or Nesterov-Steele extrapolation method, and there are numerous variants. So these methods just give you a bunch of different iteration complexity results under different assumptions and different parameters of the problem. So a question is, are they or are some of they optimal? So if yes, then great. We can head on to the next question. But if not, we'd better find some instruction or find some hint about how we can improve this complexity. So to answer this question, one thing to do is to construct the lower bound which is the minimum number of iterations for finding an epsilon point for certain minimax problem that we will carefully define later, and for some certain algorithm class that we are considering, which is also the goal of this result. So rigorously speaking, the first function, or say problem class, that we are considering is this general convex concave problem class. For this f of xy, we assume it's mu x strongly convex in x, and it is mu y strongly concave in y. And we also specified this whole bunch of different Lipschitz constants for the gradients. So the first one, Lx, it's for the partial gradient for with regard to x, and for fixed y, it's like Lx Lipschitz in x, and similarly we have this Ly for partial gradient in y and for fixed x, and Lxy, so it's for the cross kind of the coupling effect. So for the partial gradient of y, but we fix y, then it's Lxy Lipschitz in x, and similarly for partial gradient of x, we have the same Lxy. So at this point, it might look kind of messy for this definition here. So in some special cases where the function itself is twice continuously differentiable, then you can write its Hessian matrix as this one, where you have these 4 blocks of the Hessian, and then that Lx well naturally corresponds to the spectral norm of this block, and of course the maximum of that for all x and y. And the Ly is the spectral norm for this part, and Lxy is the spectral norm for these 2 off-diagonal blocks. And they're the transpose of each other, so they have the same spectral norm. So in this case, we just define this function as this one. So this whole bunch of parameters that specify the property of the problem that we're considering. So I just want to emphasize that we do not assume twice continuous the differentiability. So this is just for illustrating the meaning of these else. So if we're considering this class of minimax problem, then we also need to define a corresponding algorithm to solve that. In this case, we define the pure first order algorithm class with the linear span structure. So we say an algorithm belongs to this algorithm class if the iterations that are generated by this algorithm are lying in some subspaces. So this xk, yk are the case iterates generated by the algorithm, and these are the subspaces that it belongs to. And these subspaces are defined as follows. So the first subspaces are just the linear span of your initial point, and then later on, for the next subspaces, for example, for x, this is hk plus 1 over x. It is the linear span of all the previous x iterates and all the previous gradients, partial gradients with regard to x. And we should notice that here, the argument for these gradients are not necessarily our previous iterates. It's just some points belong to the previous subspaces that will be okay. So this will enable us to do some linear combination between the previous iterates and compute the gradients there. And similarly, we can define the subspace for y as follows. So this algorithm is actually quite general. It includes most of the important algorithms, including the gradient descent ascent or its alternating variant, and of course the extra gradient or mirror prox, or you can optimize one side to certain accuracy. For example, you first maximize over y using the gradient method for accuracy, and then you just alternate to minimize over x, and then you just alternate between the two. Or you can have some different variants for this multi-loop algorithm. So now let's see some detailed examples and the iteration upper bound provided by them. So in this case, we just define the mu to be the minimum of mu x and mu y, and this L to be the maximum of that whole bunch of different L's. So the first, simplest case is the gradient descent ascent. So at the tth iteration, we just do one gradient descent step for x and one gradient ascent step simultaneously for y. And then if we choose a proper step size of this order, then you'll have the L square over mu square iteration complexity upper bound for finding a solution that has a duality gap less than or equal to epsilon. So for this algorithm, it is not optimal, and this L square over mu square dependence is actually quite bad. Another algorithm is the extra gradient method. So different from the pure GDA algorithm, it first computes another point. I'm not sure if it has a formal name for that, so let's just call it prediction point or anything you want. So it first computes this kind of prediction point by a single gradient descent ascent step. But instead of using this point as your next iteration, you actually go an extra gradient step that you compute the gradient at these prediction points, but you go on your previous iterates. Although this looks a little bit weird, but for the minimax problem, it indeed improves the gradient descent ascent algorithm. And it turns out you can choose a much more aggressive step size. You'll have the L over mu times log 1 over epsilon iteration complexity. And under some special parameter regime, this is actually an optimal algorithm, and it matches the existing lower bound for min-max problem. However, under the most general parameter settings, there are some cases that this is not optimal. A similar algorithm is Nesterov's dual extrapolation method. So this method, compared to the simple gradient, extra gradient, it can handle the simple constraints or some possibly non-smoothness if you have the availability to some proximal operators. But the original algorithm is kind of very complicated and counterintuitive. So we just put its most simplified version for unconstrained min-max problem here. So we can show that for unconstrained problem, it can be simplified to the following form, which is a mixture between the gradient descent ascent and the extra gradient step. So in this case, you also have this L over mu iteration complexity times log 1 over epsilon. So after seeing this single loop algorithm, we can also have some double loop algorithm. But for the sake of time, let's just skip this part. So for this function class, and for this for this function class, and the pure first order algorithm class with linear span, we actually have the following theorem. That is, for any epsilon greater than 0 and any algorithm in this algorithm class, then there exists a bad problem instance in this problem class, such that at least this number of iteration is needed by this algorithm to get an epsilon small duality gap. So if we carefully look at this lower bound, we will find it's actually quite interesting. So for this part, Lx over mu x, and this part Ly over mu y. In this case, if we just consider the minimax problem that have absolutely no coupling, for example, minimize over x, maximize over y, fx plus gy. So in this case, you have absolutely no coupling, and for the strongly convex concave thing, the known lower bound for strongly convex optimization is square root of condition number times log 1 over epsilon, which is exactly these two parts. So intuitively, these two terms kind of corresponds to the hardness of partially minimizing or maximizing one side of this minimax problem with the other variable fixed. And then we have this term, which characterizes the hardness of the coupling between x and y. So in this lower bound, when the coupling is very weak, then for example, this Lxy is far smaller than the Lx or Ly. So this term will be dominated by these two terms, meaning that we're kind of having the min-max problem that is always decoupled, almost like two separate optimization problems. But when the coupling is kind of strong, then the middle term will be dominating. So this will kind of the term that measures the hardness of the coupling. But unfortunately, for this lower bound, at this moment, we don't know if it's tight or not. All we can know is under a bunch of special cases, it is tight. So as we have mentioned before, for two separate strongly convex problem with no coupling, this lower bound, it is tight, and it is achieved by Nesterov's accelerated gradient methods. And for another special case, that is for all the L's, they're of the similar order. All the mu's are also of similar order. There's no extreme imbalanced case between these parameters. So in this case, we can simplify the lower bound to this guy. And if you remember, this lower bound is achieved by extra gradient and the dual extrapolation kind of method. So under this special case, our lower bound is tight. And under the most general parameter setting, we do not know an optimal algorithm that matches our bounds. But fortunately, one of the following up of our results actually achieves a bound that almost matches our result. So instead of the Lxy square, here they have an L here, where this L is the maximum of the of these three L's. So for this case, we can say it is almost tight, but still there is a small gap. So so this is still an open question about the tightness of our lower bound. So this is one special problem class, an algorithm class. At this point, are there any questions?
Yeah, I have a question for your bound result.
Okay.
So you consider this general class of mixed problem, right? Your coupling term can be non-bilinear. So if the coupling term is a bilinear form, like you have y in the product with A matrix times X, just that term, that
Okay.
this lower bound is still hold?
The lower bound is still the same because our worst case instance is a bilinear coupling case. Well, it is actually a quadratic minimax problem.
Okay, I see. So even your coupling term is bilinear, the lower bound.
Yeah. Yeah. But when the coupling is bilinear, you can have some other algorithm class that achieve better lower bounds, and that is tight. So that is exactly what I'm going to talk about later.
Oh, so you're saying for bilinear minimax problem, the upper bound is the same as this lower bound?
Not this lower bound because we'll use some other algorithm class.
Okay, okay.
So when you purely use gradient information, the tight upper bound is not known yet.
Okay, okay. Okay, and also for your next slide, you mentioned the upper bound with a big L in the middle term, right?
Right.
I think this maybe it shows your bound is tight because you can scale your problem at this L, right? You can always scale that. Then your Lx, Ly, and mu x, mu y are both scaled, just like you divide L. Then that L will appear in the log term, right? If we scale back.
Okay. Okay.
Right. So sometimes your bound is right, I think.
Right.
Yeah.
Right.
Okay, thank you.
Yeah. Yeah, that's a good idea. I'll definitely consider that later. Okay, so that is one problem class that we're considering. And well, the next simpler problem class is exactly this bilinear coupling class. That is, this objective function f of xy can be written in this way, where f is a mu x strongly convex function and gy is a mu y strongly convex function. So this is minus gy. And these are kind of two completely separable terms. And the only coupling here is this bilinear term. So x transpose ay. So here we just assume f to be mu x strongly convex, not necessarily differentiable. And gy is mu y strongly convex and also not necessarily differentiable. So we do not use their gradients. And we just denote the spectral norm of this coupling matrix as Lxy. So in this case, we just denote this function class as b of Lxy, mu x, mu y. And unlike the previous cases where we use gradient, so in this case, because the f and g are kind of completely separable terms, so we assume we have the access to their proximal operators that are defined here. That means we have the either analytic solution for these optimization problem, or we can just ignore the complexity in solving them. Just view them as some oracle. So in this case, we define the proximal algorithm class with the linear span structure. So, for this algorithm, we say any algorithm that belongs to this algorithm class, if the iteration generated by these algorithms are also lying in this subspaces, but defined differently. So the first ones are still the linear span of your initial solution. But your later subspaces, for example, for X, it will be the linear span of all your previous iterates Xi, and also all the output of this proximal operator, where in the input for this proximal operator, this gamma I or some arbitrary real number, well, usually arbitrary positive number, sorry. And this x hat I and y tilde I are just any points belonging to your previous hyperspace subspaces for all I between 0 and k. So this is your subspace for x, and similarly, you can define your subspace for y. So at this point, this proximal operator might look a little bit weird to appear here. So actually, if we take into account the spatial structure of this problem, we can just equivalently write the proximal operator as the argmin of this minimization problem. So this is exactly our minimax objective function with y fixed as this y tilde I, and with an additional proximal term with your proxy center as this x hat I. So this is kind of partially optimal x for any fixed y. So so the subspace for x will be the linear span of these x. So for this algorithm class, we'll just give you one example. So this is the optimal algorithm that we're talking about. It is derived by Shenbo and Pak in 2011. So in this case, they just choose constant gamma and constant sigma as their step sizes here, and theta is just some constants. And then their algorithm is kind of like this. So for any given initial point, your y will be the output of this proximal operator, where the x tilde k is not your previous iterate, but the linear combination of your previous iterates. And then your next x will be the output of this proximal operator. So although this algorithm looks quite simple, but they show that you can achieve this. You can achieve an iteration complexity upper bound of this form. And later on, we'll show that this guy is actually an optimal one in this theorem. So that is for any positive mu x and mu y, and for positive lxy. So in this case, just for any algorithm in this algorithm class, there is a bad problem instance in this problem class such that at this number of iteration is needed to get epsilon duality gap. And as we have mentioned, this lower bound is tight. So any question for this case? Okay. So So these are all results about the strongly convex and the strongly concave minimax problems. But what if these mu x and mu y equal to 0? So we'll have to define a different function class f0 of Lx, Ly, and Lxy. So these L's are exactly the same as before. But instead of mu x and mu y, we put some Rx and Ry here. So we say a function belongs to this class if and only if it belongs to the previous class with mu x and mu y equal to 0. And also, because it is this time it is not strongly convex, strongly concave. In general, the saddle point does not necessarily exist. For example, min x max y, x plus y. So the saddle point does not exist. So in this case, we will have to assume the saddle point exists, and they are bounded by this Rx and Ry. So if your minimax problem satisfies all these properties, and then we say it belongs to this problem class, function class or problem class. Yeah, both are okay. So in this case, we still consider our previous pure first order algorithm class, just using the gradients with linear span, and then we're also considering about the problem class of this guy. Then we will have an iteration complexity lower bound as this one. Just like the previous case, an optimal algorithm is also not known. And probably an almost tight algorithm might be derived from the almost tight algorithm for the strongly convex, strongly concave case by adding some quadratic perturbations. But the exactly optimal algorithm that matches this lower bound is not known. So in this case, the problem is still open. And also we can do the similar thing for the bilinear bilinear coupling class, and that is also with mu x and mu y equal to 0, same as before. And we assume the existence of the saddle point, and all of them are bounded by some Rx and Ry. And in this case, when we consider the proximal algorithm class with linear span, then we have the iteration complexity lower bound of this. Unfortunately, again, for this simpler bilinear coupling case, the optimal algorithm exists, and they're derived also by Shenbo and Polk. Well, I write 2015 here, but actually, the algorithm is the same as their 2011 paper, but they just make the analysis more refined and clear in their later version. So in this case, the everything is tied here. So any questions? Okay. So these are the 4 cases of the lower bounds for either strongly convex, or a strongly convex, strongly concave, or non-strongly convex, non-strongly concave, or with or without the linear span. The bilinear coupling structure. So if we just recall the way that we defined the previous algorithm classes, we'll see that everything lies in the linear span of some subspace generated by previous information, both for this proximal and pure first order algorithm. But a question is, for a general first order method, in principle, you can do anything you want to these informations. For example, you can take the square or square root or sine or any kind of operation on that. as long as you only use the first order information. So in this case, the resulting algorithm, no matter it works or not, probably does not belong to this linear span class. And and there are some algorithms like quasi-Newton or Gauss-Newton methods. They're quite complicated. You use your first order information to approximate the Hessian, and you will take the inverse of that. Well, we need to check that. I'm not sure if they belong to the linear span, but we have to check that. So I just want to emphasize that there could be some algorithm that does not satisfy this linear span assumption. So we would like to extend our result to the cases of more general first order methods. And so in this case, we'll have to give you the definition or how we specify a general deterministic pure first order algorithm without the linear span structure. So if we still consider our previous function class, f of theta, where theta is this whole bunch of parameters, or f0 of theta, just like this. And we say a deterministic algorithm A belongs to this class if it satisfies the following conditions. So first, this algorithm can be viewed as a sequence of mappings, as is written here. And also, we call this xk and yk, well, this is for definition, xk and yk as your iterate sequence. And this x tilde k, y tilde k are the output sequence. So your output and iterates can be different because when you're for example, when you're doing gradient descent ascent, your output at iteration k, usually it should be the average of your first k iterates instead of just the last iterates. So that will be much more stable. Sorry, much more stabler. So we just define these two sequences. And then given any initial solution x0, y0, this set of mappings, or say this algorithm A, will works as follows. So its next iterates and the next output will be generated by this predetermined mapping A of x at iteration k, where your input is your problem parameters and all of your previous iterations and your previous partial gradient with regard to x. And of course, the argument can be some more general point generated by some other mappings, but that will just make the presentation very messy and not necessary. And similarly, your iterates and your output sequence for y is also generated in a similar way by some predetermined sequence of mappings ax and ay. So in this case, we call this a general deterministic pure first order algorithm. And by some additional effort, we can show that the previous lower bounds for the algorithm class with linear span will be exactly the same for this general deterministic case. And similarly, we have that for the proximal algorithm class. But at this point, let's just skip that. So as a summary, let's just summarize all the cases and results that we have. So first, we consider this problem class, strongly convex and strongly concave general minimax class without bilinear coupling. And then we use general deterministic pure first order algorithm class. We have this lower bound this almost tight, but not tight yet. And for the non-strongly convex, non-strongly concave, but we have bounded saddle point. For this case, the pure first-order algorithm achieved this lower bound, also not tight yet. And for strongly convex, strongly concave bilinear coupling case with general deterministic proximal algorithm class, we have a tight lower bound of this. And similarly, for its non-strongly convex, non-strongly concave, but bounded saddle point counterpart, we have this lower bound, and it is also tight. So basically, these are all the results of this paper. So Yang, how much time do I still have?
12 minutes.
12 minutes. Okay. I think I might be able to briefly talk about how these worst case examples are constructed. I'll just give you some intuition about the problem that we construct. So first, we consider the simplest case of this function class. By simplest, I mean the algorithm class is simplest. And we consider the pure first-order algorithm with linear span. So in this case, for any given set of parameters, we construct this worst-case problem, which is a quadratic problem where this is the bilinear coupling term that we're having, and this is a quadratic term that we add to enforce the strong concavity and strong convexity, and these are some quadratic functions here. So in this function, there are two things to be designed. So first, we have to choose this matrix A, but A is relatively no, I cannot say it's simple, but it happens that we can just use Nestrov's matrix in constructing the lower bounds for strongly convex minimization. So this matrix is exactly the same as Nestrov's worst case example. And so this A appears in the bilinear coupling term. And we also have this A square. This is something that quite different from Nestrov's example. So we have this A square in these quadratic terms, and it has this form. And for this worst case problem to provide our lower bound, so the big picture is this. So because it's a quadratic function, so it's relatively easy to maximize over y. So it has a closed form solution. And so you have this phi of x. And then you will see that, well, actually this duality gap is lower bounded by this thing, which is the optimality gap for this for minimizing the function phi of x. And because the phi is the maximum of a family of mu x strongly convex function, so phi is also mu x strongly convex. So this optimality gap is then lower bounded by your squared distance to the saddle point. And then we want to show that this squared distance is large. So how do we do that? Back to our pure first order algorithm with linear span. So our output will be some point in the latest subspace. You can choose any point in the subspace. And then this one will be this part, which is the size of this x star, its projection outside this subspace. And therefore, as we have mentioned that, we have designed the matrix A. So later on, we will have to design a vector B such that through some Zerochain property, this subspace is very small. On the other hand, this x star, given this b, it will has a large projection outside this subspace, and therefore we can say, okay, this gap will be very large at the iteration k. So this will provide you a lower bound for your iteration complexity. So with some more details about this about the first point, the zero chain property, is that for this simple quadratic function, we can explicitly compute the gradient of that, which is just of this form. And then with this simple form, and through our iteration, for iterative definition of these subspaces, we can actually find out that the subspace for X is actually a Krylov subspace generated by A squared and A times B. So in this case, if and in this case, because our choice of this matrix A squared, we can see that for any vector v that has only the first r element being non-zero, where this er is the rth unit vector, and v only have the first r element are able to be non-zero, while the rest of the elements are all zero, then multiplied by this matrix A squared, you will have at most one more element of non-zero entry. And therefore, for this Krylov subspace, if we can choose a B such that only for A times B, only the first element is non-zero, then this subspace will be a very small subspace. It will allow the vector to have only the first t element to be non-zero. And if your x star has a large part in the rest of the entries, then the problem is solved, which is characterized by the next task. That is, we also need to design the B that the x star will have the property that we want. So first, because this is a quadratic function, again, we can just write, we can explicitly write the equation that this x star must satisfy. So our saddle point will just be the solution of this equation. But unfortunately, this matrix is quite complicated, and it's hard to. The main hardness is to give a solution to this equation in a analytic form. But fortunately, by properly designing B, we can first preserve the zero chain property that we mentioned before. We're also able to show that the x star, it has an approximate solution of x star of I equal to qi, and the error of this qi is of order q to the power n, where this I means the ith element of x star, and the n here is the dimension of the x star. So in this case, where the dimension of this x is very large, then this exponential decaying term and will actually negligible. And therefore, and one more thing is that we'll have under our choice of B, this q here is a number that is between these two monster terms, so they're quite ugly. But this part is exactly what we're going to see in the lower bound. So therefore, after knowing that in a kind of analytic form of this optimal solution, then we'll be able to see that suppose at the iteration t, our output is generated in this subspace, And the lower bound will be lower bounded by this, as we have mentioned. And of course, lower bounded by this, right? And for this guy, its projection outside this subspace is just the squared sum of all the elements with index greater than or equal to t plus 1. So it has this order. And therefore, if we require this guy to be less than or equal to epsilon, we will need t at least of this order. And when you substitute our interval for this Q, you'll get our final complexity result for the first function class and algorithm class that we introduced. Okay, thank you.